this thing, and let's stop the music because we don't need music. Yeah, hello. Hello everyone. So
okay, Brad, what's the plan for today?
What's the plan for today? Okay, so the plan for today is we
don't have a plan.
Wait, okay, yeah, we don't have a plan. Yeah. But other than that, I sort of have a plan, like a broad strokes kind of plan, but you're like sitting on it. Over it. So okay, let's fix that actually, because let's see. Hello, Hassel. So implementing proof. Would this be better? Sequent. Okay, let's this maybe. And this.
Yeah.
Okay, cool. Yeah, so that's the idea. So last time we tried to explain what Sequent Calculus is.
And which Sequent Calculus for minimal logic we're gonna use.
Yeah. I think we're a bit low. Let me fix that, or try to fix that. Yeah, this should be... Yeah, I think we need to be closer to the microphone. Let me... I don't want the gain to be too high. So yeah, we need to talk a bit louder.
Like this?
Nope, because it has to, like, you should talk close to here and I should talk close to here. Hello, Vince. Hi. Alrighty. So...
Right.
Okay, so... Okay, let's test if the tablet still works. No. 1 second. 1 tiny second. This should be it. There we go. Tablets. We have the tablet screen as well. There we go. And we can show and hide it. Cool.
Yeah.
Okay, so the plan is we'll kind of... So last time we went through the theory. She's a little quiet. I think she's talking like I'm shouting.
Yeah.
Hello, Alex, by the way.
Hi.
Yeah, I think you just need to talk a bit louder.
Yeah, okay, I'll try. Thanks.
Okay, so the idea is we... perfect. Right, so the idea is like last time we did some theory, only theory, and now we'll try to implement it. So it kind of like revisits the theory like bit by bit, and then as we do that, we'll implement it as well.
Okay, so we go through... Okay, we repeat a bit what we said. Okay.
Maybe you can do this instead for now. So let's, because maybe some people understand easier using like looking at code. So maybe we can explain what we're trying to do. Well, we start with a formula, right? Like right. Let's define the thing that we're going to talk about.
Yeah.
So one of the things we're going to talk about are formulas, right? And the formula can be like it's this ADT here, right?
Formulas in a special logic. So we speak of intuitionistic logic, right? But without bottom.
Yeah.
So that's called minimal logic. Okay.
Okay. So we can have variables, right? And we use a here, but we'll likely use strings or something like that for names here.
Now, one question. Okay. Yeah. Okay. String.
Okay. We'll see if we need some. That's why I used a, because if we need something else, it should be easy to do.
But we should use the same thing we used for types in our type.
Yeah, but that's the idea. Like we'll use independent of this. Okay. We'll probably add some constraints, like you should be able to compare this probably, because we need to compare if it's the same one, right? I don't think we need more than comparison on variables, right? And then we can test it with strings independently of the previous code, but then we can just plug in the like indexed type we have in the other place, and then it should work just as well.
Great. Okay, so we can have
yeah. So we have variables. You have implication, right, which is this thing, right? Implies, right? We can have ands, right? Conjunction and disjunction.
Great.
As or. And we have some nice little like operators, so we can write them nicer and do pattern matching and so on without using like too many parentheses or like being able to write nicer syntax. And then we have the sequent.
Right, so this is a formula, and now since we're dealing with Sequent Calculus, we're gonna use actually, instead of formula, sequence.
So okay, before we get into that, what's Sequent Calculus? Like a quick recap.
Quick recap, Sequent Calculus is a formal system which allows you to check if you can find the proof for a formula or not, which means you can show that your formula is a tautology or valid, or it always has a proof in your logic, right?
Okay.
So this is a sequent calculus. There are other types of formal systems, but like natural deduction, the one which is used in Curry-Howard isomorphism, but we are going to use sequent calculus.
Okay.
Why are we going to use sequent calculus? Because it is better for theorem proving. So it is better in order to
So at least for this logic, or at least for simple any logic, are you going even recursive logics, even
at sequent calculus, you have better chance to obtain an algorithm with sequent calculus than with any other formal
we'll
system.
get there and we'll see.
Well, yeah. but no, I mean, even for classical logic, which is the most easiest logic, right?
Okay.
Their natural deduction fail to be able to be used as with an algorithm, right? Remember the problem with modus ponens. So, because
as long as you have implication, you're going to have problems, right, with natural deduction. Not
only implication, also with if you want to think what happens if you want to destruct an OR in natural deduction, you have to guess the other formula you will imply.
Okay.
Right. So the trick is that in natural deduction, sometimes you have to use some magic in order to go further in a proof.
Okay.
With sequent calculus, and especially with the sequent calculus we're going to use, things are straightforward.
And the solution some people do is they use heuristics, which kind of make things better most of the time, but it's no guarantee that you'll find an answer. Like
ours is an experiment. We will see how far we'll get us. Maybe we will come up with we will find out that actually you cannot obtain too much using this approach.
Yeah, maybe
or like combine with an heuristic. But for the moment, we try to keep things
for the simple logic. It should be
possible.
simple. We'll see for things that are more complicated. Okay, so then we have a sequent, right? So sequent calculus is based off sequence, which basically, so what's a sequent? You have it's kind of like a syntactic construction. Is that fair to say?
Yeah.
You want to share the tablet?
Sure.
Where you add this sort of operator, this fat arrow, right?
Right. So that's a metalogical symbol in the sense that it's not part of your logic. It's just a notation that makes things.
It allows you to use this the sequent calculus reasoning to.
Yeah. Exactly.
And we use this to sort of split a left hand side versus a right hand side. Right.
And left hand sides are hypotheses, and the right hand side are conclusions.
Yeah. So on the left hand side we have an array of formulas, right? A list of formulas, a set, a bag, or whatever we want.
Yeah.
It's not actually a set because we can have duplicates, so that's
right.
why it doesn't really matter much in the current logic that we're using.
No. I don't think that's not completely correct what you're saying. So the point is that first of all we have to fix the idea that there isn't just one sequent calculus for a logic. You can have several sequent calculus, and of course you have to show that they have the same power, right? So and in our implementation we are going to use a very You
have to take it?
I think it's the delivery guy.
Okay. Do you want me to go or do you want to go or?
I go. We can ask.
You can ask him to just leave it somewhere. Okay.
Sorry.
Sorry, she needs to answer. I can probably. Just next time that I need to watch streams, the streams I've missed. Be right back. No, I don't think you do, because we were going to go through most of it. Let me hide this thing for a second. So the idea is that we have. So on the left hand side we have a list of. A list of formulas, and on the right hand side we have another list of formulas. Although I'm not 100% sure that this should be an array. I think this needs to be just a formula for intuitionistic, but we'll ask Denisa when she's back. And the idea is again we use this notation for sequent, for the sequent constructor. It's a syntactical framework which allows you to do this is not all that there is to it, right? So for now we're only showing the data, right, part of it, but it also has some rules, right? So if the formula has a specific you'll see that we will end up something like that, right? You'll see we'll actually what we'll do now is we'll try to find proof or something, right, where or is it find proof? I think it's like prove or something, right? We're given some formula A. We can decide whether. Okay, she's back. Let's see if I've been saying
What did you do?
crazy things. Okay, so first thing, okay, before we go into this thing, so didn't we figure out that
exactly.
this needs to be not an array?
This is what I wanted to say. So for every logic you can
What did you do? Talking to the mic, by the way.
sorry. Yeah, so okay, first we said we have several sequent calculus for a logic, and we are going to use a special one which makes proof search much easier. And then for each logic you can have a sequent calculus or several sequent calculus, right? And for classical logic, the one with true and false, you can have actually several conclusions, right? So you can point out. So that part could be an array.
This part, right? The right hand side.
Exactly. But for intuitionistic logic, and in particular for minimal logic, which is smaller, we can have just one conclusion.
We have to have only one.
We have to have
it's
one
a requirement.
conclusion. Yes, exactly. That's the trick with this sequent calculus. Right. So there we have, and that will make things a bit easier.
Okay, cool.
Right.
So that's one thing. Okay, so what are we trying to do now? So are we trying to do something like starting from a formula?
Sorry.
So starting from a formula, what do we create? Right, because I give you a formula. What does sequent calculus give you? Right.
Right. So sequent calculus gives you some rules.
Okay.
Which manipulates the formulas in either hypothesis or conclusion.
Okay.
Or the conclusion, in such that you destroy your formulas as much as possible until you arrive to some special kinds of sequence, which will be called axioms, which are the one you accept, like, okay, I know these are proved, I can prove this, right? And therefore a sequent calculus, if you start from a sequent, will create a tree, right, which will be the proof, showing how you construct a proof for your sequent calculus, your sequent. And first, well, maybe we should say, before going further, how one should think of a sequence. So you can associate to any sequent actually a formula. You take the conjunction of the hypothesis, and it implies right. So the meta symbol, actually, it's good to have as an intuition.
Let's write this. So let's say
exactly.
Sequent A formula A.
Hi.
Right. Hello, Christoph. So this is what you mean, right? So for any sequent, we can create a formula.
Yes.
And this is like let's write this formula because I'm pretty sure we'll need it at some point. Maybe. I mean, it's
and we can also build from formula to go to sequent, because actually we will want to show that the formula is a tautology, and then but you will have to translate it in a sequence.
Well, it's trivial to transfer to a sequent because it's just right hand side, right?
Yes, exactly. But we could
sure. So we have a sequent, right? Formula. So a sequent is what? Is like hypothesis, right?
Hypes.
Which is an array, right?
Yes.
And a
one formula.
And how do you call the right hand side? Like conclusion? Con? Sure. Right?
Yes, exactly.
Okay. So then we want to do ands between all
exactly
these things, right?
Right.
So is it something like but like should we also have, like, what happens if this is empty?
Let me remember.
Do you need true or something?
Yeah, or you can just write. I will think about this.
I think we need
for the
true
moment.
Here, because otherwise you cannot write this.
Yeah.
So let's add true here as the formula which is always true, like trivially true, like a unit.
Okay, I will look in the book for this.
Okay, meanwhile I think I can write this thing.
Because I'm trying to see what happens if we don't introduce.
So I think we can do something like fold.
Well, I think we need bottom actually in the logic.
Bottom?
Yeah. First of all, don't write it true, write it like. Okay, leave it as you want. I think we need bottom.
Wait, but if we have bottom implies something, isn't that always trivially true? I think it has to be true.
Yeah, but you will never get to that.
What do you mean you'll never get to that?
We will not use it.
Okay, okay. You find
Yeah.
the thing in the book, and I'll write this. So okay, we need to fold L over. We need to fold L. What this operator like AND, right? With true as the over hypes, and then we need to do this implies. I guess we can do it like this. Implies com. I think this is what we do. Oh, I didn't import it. I mean, there are arrays, but maybe just use foldable just so we're sure. Oh, we are not in Haskell or in Purescript land. There we go. Yeah, but what if yeah, but that's trivial. Like how do you do it otherwise? Without typing a lot.
I'm not sorry. I'm out for a second.
Unconst the first formula and use that as a star value. But what if it's empty? Because it's an array, it could be empty. Oh.
I think we need bottom anyway.
But did you say it has to be without bottoms? Wasn't that the logic we were working with?
Yeah, but then you cannot have you will not be able to write an empty array. Well, you cannot write the formula, the associated formula. Where?
What do you mean? I can. Okay, you couldn't if you could have an array on the right hand side because that's the disjunction. But on conjunction, the unit element is true, not bottom. It's top, right?
Yeah, but it's like if you do it's like that trick in math when you do an infimum of an empty set or supremum of an empty set.
Right, yeah, I always do that.
Yeah, well, it's always fucked up.
Let me show you, Christoph, because I think if we do this...
Okay. Now we need, for example...
Right, so like we can't have this as a non-empty because in this case, this is how it gets translated.
Exactly. But then what I would do, don't put truth because then you also modify what the...
But then it's no longer...
You modify the Sequent Calculus. We don't want to do this. So put bottom. Let's do intuitionistic logic. Put bottom.
But don't you need both?
No, put just bottom. You can derive it, but... Okay, and then...
and then this is bottom?
No, wait.
No, it's can't be bottom.
Wait, so...
Okay.
You mean what happens if you have...
if it's empty.
If it's empty, then you have just A. You have just the formula con.
Without any... It's no longer an implication.
So it's just con. It's no longer an implication. Exactly.
Oh, I see. But then we don't need bottom yet.
But then you need if also you don't have the formula. Okay.
What do you mean you don't have the formula? You have a formula.
If you... I mean, there is no okay. Okay, so what I was thinking is
let's not add bottom yet, and we'll add it when we need it.
Yeah, okay, leave it like this.
Okay, so this is an array, so we can do something like if this is empty, then we'll do just con, right? And
but that's not... Yeah, exactly. Yes, exactly.
Okay, let's do 2 lines here. I don't like this, but okay. And then if it's... Wait, but can I...
But, okay, right.
Okay, then... Alright, that... Okay.
What's this?
It kind of like pretends that arrays are lists. Does uncounts, right? The opposite of counts.
Okay.
And then, like, what's the result of this? I think it's like a record type or the head and tail. Yeah. Head, tail. Then fold. Oh, I could do this, right? k of head and tail. I guess you could do just this, right?
And if you have just head, it will be...
Wait, but then, wait.
If you have
no, because I
one?
think it's the maybe, right? Yeah. Just, right? And if it's nothing... Oh, if it's just one.
What happens if it's just one?
Oh, so we need two. Oh, wait, we need all the possible options. Then it's just head. Yeah. No, we need three options, right? So if it's nothing, then we go to like nothing and con. Then we go to con. If it's
don't write implication.
Something and if it's a single value and con, then we need to do x implies con.
X.
And if it's
exactly.
X and like more
blah, blah,
X,
blah.
Y and more, then it's just X and Y and
Blah, blah, blah.
implies con, right?
Yeah.
So I have three cases here.
Yeah.
Should we just use lists like normal people? That's what this is doing. If you fill in the nothing. Aren't we missing this case if I fill in the nothing? Because oh, okay, fair enough. So nothing is just con. Why did it do that? I have no idea.
But then isn't that the first case?
I deleted the first
okay.
case.
Okay, cool.
Okay.
Yeah, so what I was thinking, so
sorry.
for example, if we wouldn't restrict the conclusions to have just one formula, right, then you could also have what happens if you have nothing on the right.
Yeah, because then you need bottom.
Then you need bottom.
Yeah, but
right.
you don't need that.
But for the moment we are safe.
Yeah.
Okay, so you also wrote the other way around, from
Yeah.
formula to sequent. If you have a sequent, I mean F. Who says sequent F?
It's a formula F.
Ah, sorry. Okay.
And then you create this sequent.
Okay, sorry. A bit aggressive. Okay.
Okay. We good?
Very good. We can go.
Okay, so this is how we go from formula to sequent. And that's fine.
Okay.
Cool.
And if
So
you
now-
apply, you obtain the same, right? If you apply
Yeah, I'm
it
pretty sure
twice,
I'm pretty sure so you get the same thing if you do you know you don't?
Isn't your
You don't.
No. So it's okay now.
Oh, because you always
Yeah.
get nothing here. So unless you do something with F, you always
No,
get.
no.
Yeah.
The question was.
Yeah, no,
Yeah,
I know. Yeah,
yeah, yeah.
that's fine. Okay, so let's see what's next. So
Okay, so
we were
now
talking about. Okay, so we have this
this is
formula.
what you said. How you can think of a sequent in terms of a formula, right?
So okay, we have a formula, right?
Mhm.
We can create a sequence from it,
Mhm.
right? And now we must create a proof, right? Somehow.
We search for a proof.
We search a proof. Sure, we search for a proof, and then we looking at this proof, we decide about some properties of this formula, right? So, for example, if the proof only has terminal nodes in a certain shape, then the formula is
But
valid.
that's not a proof. Okay, so first of all, no, I would say differently.
Okay.
Like, okay, you take your formula, you transform it into the sequent. So far
Okay.
we agree.
Yeah.
But then you start to apply the rules of your sequent calculus in order to transform as much as possible the formulas in your sequent.
Okay,
right?
but okay,
And then
so
we build a tree. And then we want to see if that tree is a derivation.
Isn't the tree the same thing as a proof?
No, the proof is a successful tree.
Okay,
Come
sure.
on, it makes sense, right? So you for any sequence you can build a tree, but not every tree is gonna be a proof.
Okay, sure.
So proofs will be trees which have special autumn leaves. I don't know, which have some special leaves.
Okay.
Right, the one that
Sure.
are axioms.
But then proof is not something that we have in our. It's not a type. It's just a property of a tree.
Yes,
Whether
we
it's a
can write like a function.
Okay,
or
so-
something that will say if a tree is a proof or not.
Okay, but I would prefer to use the
But
type
then-
named as proof rather than tree, because tree is too
No.
generic.
No,
Okay. Okay, so how does
or
this...
Or if you want, you can write derivation. And then we will see that the derivation is...
Proof 3. No, it's...
Exactly.
Okay, let's just do 3.
Or derivation if you want.
Okay, derivation, fine. Derivation sounds good. Yeah, I agree. Right, so the thing is, okay, so while we're doing this sort of... So, okay, the idea is this, right? So we'll write a function, something like derive step, which does one step of derivation, which goes from like some sequent...
One step you want?
Yeah, one, yeah.
Okay.
Because then we'll apply it multiple times, right?
Okay.
Right, so given a sequent,
it will
create a tree of
a derivation.
A, right?
Derivation.
Yeah, derivation. Right? That's what we're doing. Like, okay, so now the question is, what kind of, what's the shape of derivation, right? What can we get? Like, what type of results can this function do?
Okay, let's look back at the, maybe we should look at the rules.
So how about we just add them as we need them, one by one? So we look at the first rule, we add the derivation that we need, we write it, and then we add them step by step. Because I'm pretty sure it's just some type of different,
Well, I mean, you have to, first of all, hi.
Wait, what? Oh, hey, thank you very much for the follow. I think we had 2 follows today. I missed the first one. The first one is JV Lee Wang. JV Lee Wang. Sorry, I'm probably butchering it, but I am doing my best. I'm sorry.
Thanks.
Thank you very much for the follow. And Tiaran, thank you very much for the follow. Okay, cool. So let's...
Okay, so the derivation. You will have nodes, I mean, in the derivation, right? Which can be either a middle node or a leaf. So you need for sure to have leaves.
Okay, we definitely need leaves. Okay, sure. Like this, right?
Right.
But this probably be the last thing that we write the rule for, right?
Yeah.
Okay.
Or the first is the easiest.
Sure.
Well, but we will see because actually
it will make sense later, I think.
Because okay. But they are the most important. Because
they're all important.
They will tell you if the derivation is a proof or not.
Yeah, but like, why do you give value to different sort of rules? Any missing rule?
I'm biased anyway.
Any missing rule will mean that it won't work, right?
Okay.
So let's look at the tablet.
Now you want to look at the tablet.
I mean, don't you want to show me the rule, the first rule that we'll
no,
do?
but go back to the.
Okay.
Go back to the code. Shouldn't you make the size of the font a bit bigger?
No, it's way bigger for them. This is their whole screen.
Okay.
Like it's the font size is like this.
Okay. Right. So you can have leaves, and then you can also have.
Are you? So Denisa is a.
I'm in neither of them. That's the truth.
Well,
Logicians are not either nor mathematicians nor computer scientists. So.
You're a teacher at the local university, and you.
Yeah, I teach classes for computer science students.
But like you do research in logics mostly.
Yeah, which is neither computer science nor math.
Or both, right? It's neither or both.
Depends on the grant you want to apply. No, sorry. So yeah, I'm doing research in logic, but I teach for computer science students, and Vlad is a computer scientist.
I'm a programmer.
Okay, I wanted to say a programmer, but I didn't want to.
No, I like the yeah. You could have a generic tree-ish thing and have the rules be separate data type, or you could have derivation. So that is my student. So I don't know. We'll see. I think we'll need to encode rules somehow, but I won't bother with that yet, and we'll figure it later.
Yeah, let's figure out later how we do. What I wanted to say, okay, let's look at an example of a derivation. So let's go back to the tablet actually, right? So
want to look at the example we wrote earlier, or last time?
Look at this example, right? So this is a derivation for this sequent, right?
So it's literally like, if you look, wait, let me hide this for a second. It's literally, we did this, right? We have nothing on the right hand, on the left hand side, sorry, they don't see that. And the formula on the right hand side, right? And if you look here now, we have...
We wanted to prove that this formula is a tautology, it's, right? And then we transform it into a sequent, right? By doing this, having no hypothesis here. And then we apply, but for the moment take it as it is, we apply the rule. Some rule. And actually last time we got a bit frustrated because we wanted to apply a rule called contraction, and we didn't apply the rule. And
we're using a Samsung Galaxy, like an Android tablet.
I don't think it's the best tool to use for this kind of presentation, but yeah, and like we're using Let's View or something it's called. It's a like desktop app that also has a tablet version, and there's just like some screen sharing via Wi-Fi. Yeah, and actually, yeah, okay, thanks.
Oh, thank you very much for the bits, Alex.
Thanks. Right. So last time we were quite frustrated, or at least I was. I was super frustrated that I couldn't apply my contraction rule, and actually it was because we were using a different rule for implication, one that I didn't have in mind. So actually this was the rule we were using for implication, and the one I had in mind, which were forcing us to use contraction, was using a different set of formulas here in the hypothesis. So that was the problem. So this derivation is true, really right? Right. Sorry, I needed to take it out of my chest. I felt so
confession
bad.
Time.
Yes, it was like my confession. Sorry.
Okay, so let's
start with the first
derivation. Rule. So what's the first rule that we wanted?
Wait. Okay. This will be a derivation, right? And we just wrote the leaf, which are these guys here. But we will also have these intermediate nodes, right? Which can have either don't we want to write this before?
No.
I mean,
why? Like we look at the first rule, and if the first rule needs like this sort of list like thing, then we'll add the constructor to derivation.
Okay, then I'm confused. So starting from a sequence.
Thank you very much, Barry. Thank you.
Hi,
really
thanks.
Appreciate it. Okay.
So starting from a sequent, we want to destruct it, right? As we said, apply the rules, right? So you end up having this kind of tree, right? And this is the root, right? And how do you? Okay, so I have this. What do you have in mind to go to the next step?
Like this function. We have a step, right, from sequent to tree or derivation.
Okay.
Right, because like.
Okay. I see what you're doing. Okay, let's look at that. Okay, let's look at the derivation step. Okay, I see what you mean. Okay. So.
Cool. So then let's write the first rule, right? Rules. Yeah, but let's look at one rule. Let's write one rule.
Okay.
So pick one.
I agree, but it matters the order in which you pick.
Sure. Like,
so I will pick in
so
the order I want.
You either pick the right order, or like as we write things here, we can just tell me to write it on top of that, write it below, or whatever. So you pick whatever order you feel is better.
Okay, I will pick the one that I think should go first.
Okay.
So the idea, if you do it by hand, I mean, I think from the result you get at the end, it doesn't matter the order in which you apply the rules. Okay. So it shouldn't matter.
Okay.
Right? So we could just write them in any way, any order we want.
Okay.
But I think from playing a bit with writing proofs, that if you go on a certain path, you end up quicker to an answer. So I think you could optimize a bit.
Sure.
Right?
So, I have no idea.
So that's why.
Okay, so what's the first rule? Show us the first rule.
What I would do, I would look at the conclusion.
Okay. The leaves are the axioms, and the initial formula you wanted to prove its tautology is the root.
Yeah, exactly. Right. So I would look at the conclusion of the sequent.
Like draw us the rule, like write the rule on the tablet, and then we can try to implement it.
Okay. This. let's look at this. Come on. Sorry.
Doesn't let you.
Doesn't let me write. Wait. Sorry. Ready? Okay. Okay. Sorry. Okay. Let's implement this rule.
Okay.
So this rule says if I have an implication on the conclusion of my sequent.
Should I do? No.
Yes.
Okay, I could do this instead. Give me. I could make this smaller, maybe.
Yeah. And put it
Is
on
it
the
too
right.
small? No, because I'll just write here. It's fine. I'll just be mindful of where I'm writing the code.
Do you use what we have on our head?
No, but it won't be like this. You mean?
Yeah.
Yeah, I guess we could do this. Because the code shouldn't really go past.
Sorry,
this.
I know I destroyed
No, that's
your
fine.
framework.
That's totally fine. I think we need to do this for a bit. Yeah, there we go. Okay, cool. So let's see. Ruined. Yeah, stream is unwatchable. Unsubscribed, unfollowed. Okay, so let's see. Derive step.
Right.
Okay, so we have a big case right here. Yeah. So if we have what? If we have some sort of like context, right? Or we said hypotenuse.
Hypes.
Right, and then we go write this to
right. A implies B.
A.
Big.
No, that's not like A. Like capital letters are constructor names. Variables are lowercase letters, so we cannot use capital letters.
Okay, but you missed 2 points after the implication.
Yeah, but you still got something wrong. No, that's fine. But unfortunately, we have to use this here because that's the syntax in Purescript. So,
wow.
Yeah. There's a lot of arrows here. Right, so in this case,
we want to go to this sequent.
Okay, so now we immediately see that this is not a leaf, right? Or is it a leaf?
It could be a leaf.
Oh, it's a leaf, yeah, because it's a single...
No, it's not a leaf. It could be a leaf.
Okay, because we don't know if it's...
This is what I'm saying. I don't know if...
I don't think we need leaf. I think we need like next, A...
Well, I mean...
No, it's kind of like next derivation of A. Oh yeah, and I think we need leaf A then. Yeah, that's...
Can they see your t-shirt?
I'm not sure if they... Yeah, probably. I'm not sure. But it's probably reversed, so... It's just a flash one, yeah, exactly. Okay. Yeah, so I think this is it. Like a leaf would only have a formula at the end, whereas... Or a sequent or something, I guess. Yeah, but the next has also derivation. Yeah, I think that's the difference. Trust me. So we need to do this.
You're no doctor. Okay.
Next, and then we give it a sequence, right?
We give a sequence. So we take the hypes we had, we add A.
So we give A and the hypotenuse. Hypotenuse, yeah. Hypotenuse.
And then
okay,
B.
And then this is just B.
Right.
Okay. Are we there yet?
Okay. So this is one. But then I'm still confused when you will transform something which is okay. No, okay.
We'll figure it out
It's
later.
It's good. Okay, let's do the leaf case. Leave the leaf there. Okay, let's do the leaf case.
Wait. Oh, right. What? Okay, wait.
I cannot help you.
Oh, because this is a derivation. This needs a derivation. Yeah. No, so let me think. Do we need? Should we do this?
Yeah.
But then.
Okay, put the.
I mean, this would work, but.
Let's do the leaf case. Let's do the leaf case.
Let me think for a second. Should it be just next?
Let's do the leaf case.
No, it can be next day. Because this needs to be like a list. Yeah, I think that's what we need to do.
But shouldn't you write the ref step of next of that? I mean, next isn't the construction for your derivation.
Yeah, but you derive sequence, not steps. Tips on JavaScript backend development. Thoughts. I got into that several times before. I'll get into that at some point later, but I don't think that's a good time right now to go into that.
Come on, we can take a break.
Like I don't do JavaScript, so if anything, it would be Purescript backend development, which I think is totally fine. So that's my 3-second take. Yeah, like I don't. Yeah, I think it's fine. Most of the time, it's as good as Haskell because you're IO bound anyway, and Node is very fast. That's my slightly longer take. Yeah, okay, let's do it. Okay, so you said you wanted to do leaves next?
Yeah, no, to write it before. Okay, and put it before this.
Okay.
All right. So if we have, but how do you, how can you see if in the conclusion you have just a variable, a propositional value? You write variable A?
Yeah.
No, we cannot have a derivation that starts from multiple sequence. No.
No, so I think what we'll have here is like branch.
Yes. Yes.
In which case we'll need to like
yeah.
We'll need to like distribute the derive step over both.
Yeah.
I think that's all the cases we have that exist.
Yeah. Okay, so
okay,
let's do the leaf.
How does the formula look like?
Well,
which
it's
one
not
is it?
exactly like this, because okay, I have this kind of axiom. Right?
Okay. Oh, so if we have a variable on the right hand side, it's okay. If
but I'm just interested for the moment if you have a variable on the right hand side, and then we will make it. But wait. I'm a bit confused of something. So
okay.
let me explain a bit how it works, and also how the rule works. So you start to build your derivation, right? And at a certain point, you figure out that. Okay, and first of all, in order to be a proof, all the leaves should be like an axiom, like this axiom, right? Like this guy over here, which says that the propositional variable I have should be in the hypothesis. But sometimes during the process of building the derivation, you find out, okay, this will be impossible to be successful.
Yeah.
And we shouldn't, I wouldn't recommend to leave it to make all the derivation. And I mean, sorry.
You wanted to stop derivation or what?
To stop the derivation.
Don't worry about performance right now.
So in this point where I see two things. So we take the sequent and you build your derivation no matter what happens, and then you look at that derivation and see if it is a proof or not.
Yes.
Or you take your sequent, you start to build your derivation, and you figure out that you will not be able to.
Don't worry about it. Like, why does it matter? You're a mathematician.
Okay, so we build the derivation.
Yeah, we don't care.
No
we'll
matter
build
if it is.
Yep, we'll build everything.
Okay.
So in this case, I think the idea is that this is a leaf, right?
It is a leaf, and you stop, and then we will look at this at the end.
We'll check if the leaf. We'll check if this variable is inside this, right? That will be the.
No,
I don't think so.
This Sequent Calculus has quite smart rules that avoid loops. So I think we will not get into a loop, no matter what.
But like we put this thing in it, right? Like the whole thing as it is.
Yes,
right?
exactly, because we need to check.
Right. So we just, if this is like a termination
That's a leave
step.
and we terminate.
Okay. So right now it's telling us that we're not handling and ors basically, right?
Okay, so the next point I would look if you have an and on the conclusion.
Okay. So if we have an and here, right? So A and B, right? Like this? Okay, so what do we do here?
We do this. We split. We move to branch.
So this is a branch, right? So it's like branch with hypothesis and A, and then the same with B, right?
Yes, exactly. This is what I wanted to say. That we need.
We will need that
later. We will need them to see. I mean, also for our sanity when we want to check our results. So I would add to each thing you have in your derivation to say
the rule name.
Okay, you cannot have it for the leaf, but you can have it for the next and the branch, and it will tell you how you ended up there, right? Yes. Yeah.
So do we have should we do just this, like
just write their names, right? So we write their names, and then in the next and in the branch you make. Okay, so
but we put it here, right? So rule here and here, right? Or something.
Thanks. See you.
Okay, thank you for dropping by and for the bits, Alex.
Yeah, exactly.
So
rule.
Let me remove the one from the end. Oops, I have no idea how I opened that.
Yeah. Right, and you have right end, right left end. Just write R and end, like conjunction. Right and left end and right or and left or.
And then
okay,
implication, right?
We don't have. And then for the implication, write R imp. And then for the left, we have 4. So we have L0 imp.
What?
We have 4 rules. In the case in which you have an implication on the left, you have 4 rules.
Okay.
And then left or imp, left and imp, and left imp. Impl.
Like this?
Yeah.
Okay, what's the problem here? Oh, I think it's not an error here. Okay, so then this we need to give it the rule name here, right? So the rule name for this is what?
Rimp.
Rimp. Okay, and then the rule for here is R and?
Yeah.
Okay.
Cool.
So wait, what's the problem here? Derive step. Oh, okay, it's the same problem. Okay. Okay, so what's the next? Can we do or?
Yeah, let's do or. Okay, let's leave or at the end. The last one.
Okay.
Okay, let's do left. Let's look at this guy. Here, this one. Have left on. Okay, but now, this is how.
Okay, don't say how you get an and on the left hand side now.
Yeah, so since you have several hypotheses, the trick is you want to search for a formula in your hypothesis that have an end, right? So all these guys here are our hips, and we want to find one of them.
Ooh.
In which we destruct and then create that sequence.
Ooh.
So for the conclusion, it's easy because you have one.
Ooh, that's nasty.
Find the first, but then, that would work. Just take the first one. But then, as I said, sometimes when you apply the rules in a certain order, it will be easier. And
but this is like, okay, the problem...
and moreover, there are some cases in which,
So I think, okay, the problem is you cannot pattern match on that. So since you cannot pattern match on that, I would probably leave that as the end in a way that, okay, if none of
this
those...
This is the core now.
What?
I mean, this is the crucial point to split the hypothesis.
But you cannot do this. You need to do that last. You
No.
cannot do... What do you mean no?
What are pattern guards?
And then, okay, I see. So you're saying something like clips A and do this, and then have here something like making sure that we can find it. And then don't have an otherwise clause. And then if this isn't true, then it just skips to the next case match. I think that's how it works. Where is there a like... Huh? You mean we can do this? Wait, no, you can't do that. You keep going for a while. I'll write up a guest. Do you mean put it in the case here? I don't think that's what you mean.
Okay, we can think while we wait for him. We can think what happens if we have disjunction on the right. So the trick is when you have disjunction on the conclusion, you have, because actually for a sequent we will not have necessarily just one derivation, but you can have several derivations. And this split is
like this,
caused,
right?
Yes, and this split is caused by having a disjunction on the conclusion.
Okay.
So in this point, what we built here is a list of derivation. So a derived step can be a list of derivation.
Okay.
Right.
So I need to change this, right, to this, right? And we need this to be like a like all of these are just single, right? But this one gives us multiple, right? Wait, I don't think we can do this.
But yeah, and remember, I don't know how it works, but you have to. So look, when you.
1 second, I find the import.
I don't think it's that easier.
Why can't I find data list here?
But wait, before you write, listen a bit. Let's look at an example.
No, it's fine. It's just a list. It's fine. Don't worry about it.
It's not a list.
What?
Because at the end, when you want to, it's not a list. Okay. I mean, I don't see how you. Let's look at an example, because I don't see how you catch it with this construction.
I mean, we just...
Can we look at an example?
Sure.
Okay, suppose I want to prove this. Right?
Okay.
Apply the rule for the implication. I move the disjunction like this, B or A, right? And now if I have a disjunction on the hypothesis, it will give me A implies B or A and B implies B or A.
We don't have this rule written anywhere.
Not yet.
Okay.
Right?
Okay, sure.
We have it.
No. We have not written any rule on the hypotenuse. Sorry.
Okay.
For the left-hand side.
Okay.
Hypothesis.
You can put it. I mean, it's like it creates a branch.
Yeah, but it's the same problem that the one we were trying to write earlier, where we need to figure out how to do the find the first one.
Yeah, exactly. Right. Yeah. Okay, that's why we stopped.
Yeah.
But now the point is like here when you have this disjunction on the right.
Okay.
You want to actually instead of this derivation that you built so far, you want to obtain two derivations. One which copies everything from which copy everything from this point and will create here, for example, we'll choose A implies B, and another one which creates the same derivation so I copy what I did so far. Sorry, I don't know how to copy paste in this. Alright, so this is what I had so far, and in this point I apply the other rule for the disjunction. So I want to have both of this derivation. So this is catched by your construction there?
Yep.
Okay. You sure?
Yep.
Okay, I don't see it.
Okay, so
right.
So what's the rule?
So the rule is this: you split into these two sequence. So if you have A or B, you build two derivation. Two.
Okay, so in the cons with both of them are next. Derive step with this over A. And then pure next derive step over B. I made it twice. I'm gonna take a nap. Okay.
Okay, see ya.
Sleep well.
A nap. That sounds awesome.
Okay, so we don't know what list is. Let's import list from data list. There we go. What do you mean? I don't know what const is.
I think you forgot to put. You also need to put the name of the rule.
Sure, that's here. What's this called?
Okay. We have to we have to split it in
This one?
1 and 2. Yes.
But that wasn't the problem. That wasn't the problem. So wait, there's no way.
Maybe it's not called cons.
I mean, the opposite is called uncons. I'm pretty sure it should be cons. Am I crazy? How do you construct this thing? Why is it called why is this a sorted list? Huh? Okay, insert is over sorted list for whatever reason. Okay.
Wait, can you go up a bit?
No, it wasn't there.
Can
Okay,
you go
wait.
up?
List A. Oops. But I don't want the lazy version. So it's here, but it's not exported from here? Oh, this is the constructor name. Okay. So I guess there's no...
There was one.
Okay, so it's just the constructor name.
It was one. Did you
Where?
see it? Just go below.
Oh, it's a different type. It's infinite list.
Infinite. And the other one? The
Okay,
one below?
I can just do this.
But there was one below.
It's a different again. Okay, let's just use the constructor, I guess. Could not match list with derivation. Oh, okay, this makes things awkward. Let me think.
But my point is, I mean, I don't understand if you are from a point. I mean, can I ask you something which I don't understand? But if I'm here, for example, well, no, actually, sorry. If I'm here, how it will break into a list? I mean, I don't see how
you don't need to break into two separate things. You just branch there, the result is always two lists. You don't need to copy it effectively.
But how you will reconstruct your proof? Because we need to reconstruct it in order to have like a tree like this, because this is what we want to get back to the lambda calculus.
I mean, okay, so it will be something like wait, let me think about this problem first, because this is probably going to help with the other one.
Okay, I will take a 5-minute break.
So this gives us a list of derivations Is the tree type wrong? Should we have only A's here? No, it's supposed to be, but otherwise it's not recursive. Maybe we need to have just A's here. Because we're essentially just doing sequence. So then this shouldn't be here. We're just doing a single step here, which there's no reason to do this thing. Yeah, I think that was weird. Okay. And now let's figure this out. So what was the example? So we have a what? A or B, right? Implies B or A. And then after this we get like a derivation. So let's start with this sequence, right? And then, okay, so then we get a derivation with a single thing here, which like we have this, right? And then we get a what? We get a next, right? Next, or a single list of next. Where is it? Our imp of so we get the A, right? So we get A or B. Let's do this. Okay, goes into B or A, right? And that's a single list. So now the idea is we just map derive step, right, over each subsequent step. Oh, but then we don't keep the...
What's happening?
Wait, I'm thinking.
You're thinking?
I'm thinking. Okay, so this will allow us to find a... Yeah, we're not building a tree here. Okay, so I think we need this.
Wait. What?
Might be a distraction. I'll have a look in a second, Christoph. Wait,
we ended up with another
I'm
problem.
tired.
Why did you do this?
So I want to define a single step here. I don't want to call this recursively manually, I don't think.
What?
So, okay, the question is, should these... Okay, let me remove this. Should these A's be A's or derivation of A's?
It will be hard if we put derivation there. You want to have a sequent, right? I mean, let's try to keep what these trees look like.
But then it's no longer a tree, right?
In each node, you want to have a sequent.
Yes, you want to have a sequence, but you also need to have the next part, right? Because otherwise it's not a tree, so it's like this.
Ah, okay, I see.
Right? And then...
Yeah. Okay.
Right? We need it like this, right?
Right.
Because you want to have the sequent
exactly.
and then like the current sequent and then the like next steps, right?
Yeah, yeah.
Okay.
Yeah, exactly. Yeah. And this is the point in which I don't see how you combine.
This is not even, this is just derive. It's not even a step. It's just, it does everything. Because we have to recursively build it. Okay, so then let's fix the code as it is now. So this also has to call derive over, wait, not here. I think it's here. Here.
No, because you want, in the derive, you want to give just the sequent.
Huh? Yeah, and this, oh yeah, this is a, so yeah, it's here, I guess.
And you also want to have...
No, it's not here, wait.
Wait. You want to keep your array there because this is what you want to have in the leaf, and then you apply.
Huh?
Like,
give me a second.
Wait.
What did they?
Here you want to keep this because this is what you want to have the sequent in your leaves, and here again you want. you want to derive.
Yeah. But wait, there's something else wrong here, and I have no idea what. They forgot some parentheses or something somewhere.
What?
It's giving a very weird type error here. Oh, is derive a keyword? Okay, derive is a keyword. We cannot use that.
Derive.
Well, you don't like proof.
Build derivation.
Okay.
Okay, and
then this
is what you want to have.
And then the next steps.
No, sorry.
What?
No, you want to build. Actually, you don't. I mean, you don't want to have. Wait, I'm confused.
So okay, let's look here, right? So let's look here, for example. So we have. So we start with what? This will be a sequent, right?
Yes.
And the result.
And you will say build derivation of that.
Okay, so the result is a next. This is the next, right? This is the link between these trees, right?
Where do we keep this sequent? Where do you keep it? Where are you going to see it?
Also, should we keep it in the current one? I guess.
Because you want.
So I guess we need to store like. Oops. I guess it should be here. So there's the current one, and then do. Oh, I shouldn't have deleted that. Seq, and then. We need to do like.
And there apply derivation, right? Build derivation.
Then the problem is that build derivation is a list of derivations, not a single. Maybe you could write derivation to do one step at a time, and then fixed point. Yeah, but then I have to do like what happens if I have a branch manually.
Sorry.
Let me think. So this
Can
is
what?
Hide the tablet.
Yeah.
Where is
it? Doesn't matter.
There we go. Aren't we just doing this anyway? Oh wait.
But what's the problem now?
So we need to do build derivation over that sequent, right?
Okay.
Which is a list of derivations.
Wait, can I suggest something? Let's forget about the list. Let's just build a derivation and then we come back to the list. Let's suppose we can apply just the first rule of OR. And then we'll think.
No, because that will change a lot.
Okay.
Of things, I think. So wait, don't we just do, instead of this, don't we just do build derivation, which is a list of derivations anyway?
Better? Yes, exactly.
It's when the proofs, when you can have multiple proofs for the same thing, and you have to something like when you have OR, basically you kind of get a left proof and a right proof, and you try both.
Can you show the tablet again? Right. So, for example, in this example, when you suppose you are here, right, and you have one disjunction on the conclusion, and you either can choose B or A, and what you have to do in the Sequent Calculus, you have to just copy everything, right? Copy what you've done so far, and then either choose B or choose A, and move on with the derivation from there.
So okay, let me think. So you want to build a derivation starting from that thing. Isn't it just this? Yeah, that's the plan. I think it's literally just this in this case. And then in this case, I think it's
Wait, you have to call build derivation again, right? So
yeah.
put the sequent you have.
Okay. And then this. Oops. Okay. And then here we have this. So this is no longer a branch, right? This we just get two lists.
Yes.
So okay, we have this one which is build. Oh wait.
But you still need to put the
Build derivation over what?
that one. That's okay. Type simple.
Is that all?
Yeah, but you also have to put the sequent as well in
the one. Oh yeah. Where is it? Here, right? Okay. And then it's 2 and B, right? Oops.
But you have to write next the name of the rule and then the sequent.
I think we just append them. Yeah, I'm pretty sure we just append them.
I'm looking forward to see how you will be able to print the tree at the end.
Me too.
I'm so hungry.
You're hungry?
So hungry.
Okay, so what else do we do now? Okay, let's look at like
let's look at the
Christoph's
example.
Example here. Okay, you have different type of formulas. Sequent is okay. You like records. We get it. Okay, so okay, but then like if this doesn't match, so okay, this is like you're kind of bunching them together, right? Okay, yeah, okay, I get it. So you're saying, okay, so what was the thing that we were trying to do before that we couldn't? We were looking for
and, for example.
On the left hand side, right? Like this, right? And we wanted to do something like that's the syntax, right? Yeah, and we wanted to say something like, okay, so if it's just and formula,
That's as you find it, right?
Yeah. With find map match and okay, you're using this thing because you're also mapping after you find, right? Okay. So this is a like foldable thing. Yeah. Okay. Find map over. Okay, we can do that as well. Match and hips. Then we can do something here, right? Which is what?
Okay.
Oh wait, instead of and, I guess we could keep it. I kind of like that. That's fine. We can use AND formula here. Okay. So what do we do here?
So.
Oh yeah, we do. Okay, we do the list thing, right? Where we do. Oh, but then we need heaps without that, right?
This will give you back the formula, the AND formula.
Yeah, but it doesn't give me heaps without the AND formula.
Oh, you can keep it.
Oh, it doesn't matter if you have duplicates.
Doesn't matter.
Yeah, but then next time we'll find this the same thing again.
You create a loop. Yeah. You need to delete it. But can't you modify match and no.
I mean,
can't you throw away?
No. I mean, we could
you
do something
like.
like
your own function that will delete the AND formula from the heaps.
Yeah, sure, we can, but it's a different thing. You can do this. You can do both at the same time.
But be careful not to delete it. I mean, you can have. Don't delete all the copies. If you have 2 copies of
doesn't matter. Right now.
It matters.
No, it doesn't.
For the Sequent Calculus, it matters.
Why?
If you have.
Because we're not consuming. The rules are such that we're never consuming, so it doesn't matter how many copies you have.
What? I'm saying from the heaps, if you use the formula A and B,
okay,
right? It can also there can be another occurrence of that formula A and B.
Okay, and we need to remove all of them.
No, just one.
Why? Because it's not a linear logic. We're never consuming from the left hand side, ever.
Okay.
Right? Aren't the rules such that it doesn't matter if you have copies or not? Because we're never consuming things when we're using them. Like, this is explicitly why we didn't need the contraction rule. And
No,
that. Because like we don't have rules to duplicate
it's not
things.
construction.
And neither to throw things away.
It's not construction, it's weakening. Construction we are using, but it's built in the rules.
Yes, okay. We don't need them because we're not throwing them away, so we don't need multiple copies. We only need to copy things if you throw things away. Okay, so we need to build a next of what's the rule name? Left and?
Yes.
Rule for next
Put the name
and
of the
seq, and then overbuild derivation with okay, so we know that this is easy, right? This is always con, right? Oops.
Con.
Yeah, oops. Right, so here we need to start with heaps, right? And we need to do what? We need to remove delete.
We also have to better match on N formula. You need the left.
Yeah, no, I'm thinking. But then, yeah, it won't work like this. So I need to do something like... actually, no, that would be fine. I think we can still do this anyway. Like this, right? And then we need to... You know what, I'm being very lazy today. A like this, and that should work. And we need an extra, some parentheses here. Like this. Right?
Should we write the match end?
Yeah. But I think we don't even need to write a match end. I think we just need a find. Because like that was an oh no, we cannot find write that. Okay, so this is something from formula A to...
Formulas.
Sorry?
An array of formulas, right?
Nope. Because that's why, sorry, we have find map to maybe, yeah.
Oh, okay, so.
There's a problem. All right. Whatever this is result. Okay. Variable. Is the like order of operation wrong here? We need to. Do we need to do this? Oops. Okay, like this, sure. Okay, we don't need, okay, we need EQ. Yeah, I said that earlier, right, that we need EQ. We need to be able to compare. EQ formula. Yeah, we need an EQ for formula.
Hi.
Hello, me Pythoneer, welcome. So let's see. Derive instance EQ. Well, we need the name, right? Is that how you write it? All right. Okay, and I think it automatically. Oh no, it ain't. I need to do this. Okay, sure. Okay, cool. It works. Well, it works. It compiles.
Hey.
Okay, so
Let's move.
can we test something? Should these rules prove something?
Let me see. What do we have there? So we have.
But we need something very simple, because then we'll have to read something that's not easy to read.
This we cannot.
Okay, I also need to run to the bathroom. Give me one
I can
minute.
do this. Okay.
You can spend some
can I
quality
do?
time with the stream.
No, I don't know what to do. Don't leave me alone. Let's take 5 minutes break.
I mean, okay, let's take a couple of minutes of break then. I think she also needs to stretch her legs, or maybe she's scared of you guys.
Yeah, I'm scared.
Okay, let's take
don't turn it off. Okay.
Okay, I would be too.
I was think of an example.
Okay, let me make this thing bigger, because if you want to like.
Yeah.
Well, actually, that's over my. It would be over your face, so maybe. Don't have a lot of room here with.
Okay, let's see. Let's see what rules we have. So implication. Can we do? Okay, this example could be done. Checking this formula or and on the right. Okay. Yeah, we're trying to implement proof search in Sequent Calculus, and Vlad is the programmer part. I'm the one with the theoretical side. So yeah, and now we try to test what we've done so far, and we're searching for an example that we could run. So we need to implement a bunch of rules, and we have just a subset of that. So let's see what we can derive, but we don't have and okay, let's see if we can derive this. A and B implies A or B. Okay, we have disjunction on the right and conjunction of the left. That will give A and B implies A or B.
Okay, I'm back. Hey, were you nice, chat?
They were nice. I was scared. It wasn't them, it was me.
Yeah. It's not you, it's me. Sure.
Okay, let's try this example. I think let's do it on paper and see if it works. But I think we have the rules for everything here. A and B.
Shouldn't we try a very simple one
this
first?
Is simple. Okay, simple one. Try this.
Okay, let's see. How? I'm kidding. So you know what? My homework will be, regardless of what happens now.
To show a build derivation.
A printing printer for this, so that we can read it easily. Because now it will be very hard to read this.
Yeah.
Okay, let's try to see if we can.
What did you do here? No. Oh no, sorry. Huh? Nothing.
Okay, so let's do
Build
derivation of.
Apply the formula. Apply that.
That function that gives us a sequent, right? Sequent to formula. The formula to sequent. Let's use dollars because we like operators, right? We're not doing Lisp here.
Okay, A implies var A, right? You have to write like var A.
Yeah.
Variable A.
Okay, give me a second. Let's do this because I'm not gonna type S dot everywhere.
Implies. Do we parse parentheses?
It's not parsing, it's Purescript. But anyway, this is right associative, so it doesn't matter. It's fine, right? We can just write it out.
But okay.
Like this?
A.
Sorry, A.
Yeah.
Oh, okay. We don't have show instances, which we need to define. So we need for. Oh. What? Wait, why is it coming out as sequent to form? Did I type this wrong? Let me try it again. So derivation formula to sequence. So this should be a sequent of string, right? Oh, derivation sequent of string. Yeah, that's fine. That's fine. So we need okay. So we need derive generic. We don't need this generic. Edit this. Oh, I think we also need to import generic. Do we not have? Oh, it's Pago. Generic. Yeah, we do. So why can't we import it? Okay, sure. Cannot import. It does not. I don't know why it's going to YouTube.
You broke it.
Yeah.
You broke it.
There's some generic and not this one, this one. Data generic wrap. Oh, it's class generic. Okay, this is Purescript. Okay. Okay, and then we need one for Sequent. Wait, no, generic. Okay, and then I think we need one for rules as well. Okay, and then we need one for derivation. Okay, and this should compile. Oh yeah, this isn't a, this is just a simple type. Okay, now we have to go through all of this again and do show instances. Generic show, but then we have to do this and then do show, wait, no. Show formula. Okay, where show f equals to generic show of f. Oops. I think this should compile. No type was found for show A2.
Shouldn't be show small.
Nope. Oh, I think it needs this. Okay. Error wasn't great, but luckily we guessed. Okay. Oh, not this. Wait, this should. Oh yeah, that's fine. Whatever.
Whoa.
What?
You got me dizzy.
Think that's should work. Yes. Same for rule. Okay, but this is doesn't have an A, right? And now let's take this one. And this is the last one. So instead of sequent, we need derivation. Okay. Hurrah. Okay. So let's try this again. We got some answer. So okay, let's see. What's the type of this? Give me a second, because we can make it better. Have the technology to improve it.
Can you at least?
No, it's effect log. Okay, I don't know where log is. Effect class console. Okay, I think it's just effect.console actually. Okay, so if we did this, huh? Okay, what's the type of this again? Oh yeah, it's log, it has to be log show or something. So it's from A to effect T. Oh, it's traverse. Where is traverse? Data something, not you. This. Okay. It's always traverse. Okay.
What did you do?
It still doesn't help. It doesn't help.
Okay, but let's look at the leaf.
Okay, you know what?
Let's
just copy this and try to like
exactly.
print it out, like edit it in a file. Huh.
up good. Yeah, it's good. So if you look at the leaf,
So wait, let me. I don't understand what you're saying.
Okay, just split it by rule. So that's the next. That's the first part.
So this
is the sequence you had.
Like the initial sequence, right?
Yes, exactly.
Okay, and this is the next part of the rule, right?
Right. And then it has
this rule.
And it will apply an implication, and then that moves an A on the left hand side.
Wait, you're moving too fast for me. I know that's fast.
Well, you got me dizzy earlier, so okay. And then applies this rule, and then apply a sequence. Yeah, it's done.
So it's correct?
Yep.
Ha! Nobody believes us, but it's...
this will be
Oh, but I guess you're looking at this, right? At like the rule names, right? Implication.
No, and I was looking what ended up in the leaf, because that's the important part. And this will be an axiom because A appears on the left.
So if you have a variable here and then you have that same variable here, then it's the correct. No, so you know what it will be. So
let's check another example.
Let's check another example, and then next time we will. I'll write like for next time. I'll do my homework and write a pretty printer. So then we will like be able to easily read this thing, right? This sort of thing.
Yeah.
And then it will be a lot more clear.
I
think. No, don't worry. I think if you tune in next time when we have the pretty printer, it should be pretty easy to follow. Because right now it's pretty hard to follow everything with like all the types and the complicated types and so on. But I think next time it should be.
Okay, let's see.
Okay. Let's do another test. Okay, so what's the term that we want to test?
Let's do it on paper first.
Don't do it on paper. That's why you wrote the implementation.
No.
It's on GitHub. Let me. And I don't remember if I have a bot command for it. Is it PTT? I don't remember. I'll look for the bot command. And anyway, I'll paste the. Let me do this instead.
And look, we have an example which will have two implementations. Blah 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 blah. And then
I don't remember what the command is, but okay, let's add the Type Theory Tuesdays command. There we go.
Okay.
Okay, so what's
the?
So we have. We have an implication, right? So we have. Oh, can write it like this.
B? No. What? A and B implies A or B.
Okay.
This is something with list. It should have two elements.
But would it parse it correctly if I type it like this?
Yeah. Disjunction. I think you need some. Yeah.
Would it? Oh, we need parentheses. Oh, we need variable everywhere.
I'm excited. Let's check. See, we have two.
Yeah, it's two.
Yay, good.
So I told you. You are not trusting my list thing.
I still don't trust your list thing.
What do you mean? You're literally looking at it. Okay. So we have two branches. Why are they different sizes? I would have expected them to be the same size.
But wait. I think something's wrong.
Okay, let's see.
But in which order does it apply the rules?
In the order we wrote them. Okay, so it's okay. Let's take it easy. So we started from here, right?
Right end. But what do you mean right end? We had a right. No, it's wrong.
What do you mean it's wrong?
We had an end on the left.
Maybe I just.
Okay.
Yeah, because I just said right. What do you mean on the left?
I mean,
no end.
You wrote a disjunction on the right. On the conclusion, we had disjunction. The first rule
should be implication. Wait, it should be. Yeah, maybe it's a parenthesis. So we want one here, right?
Yes.
And one here, right?
Yes, exactly.
Because I'm not sure. It might.
I think you need another one.
Anyway. Okay, it looks different now.
Okay. Delete that, that's wrong. Okay, so we have an implication of...
wait. Okay, so yeah, we have two things. Okay, wait. These are the
good.
two things, right? These are the two things.
Okay, that's good.
First of all. Okay, so then we have a implication. Okay, and this is
we have a sequent.
And then we have, this is the next part, right? And then we have an and.
Can we look at the other part to see if it is the same?
Sure.
So I will trust your... Okay, an implication. Okay, it has the same, right? Right. Yeah. This one with... Yeah.
Yeah, it looks the same, right?
Yeah. Right.
Sorry. And then left.
Okay,
and.
let's go up. So applies left and, which means it will to that sequent, right? And wait. To that sequence, and then it has an R or 1 to that sequence, and it will get a leaf. Yeah, so seems good. Let's look on the other one.
Okay.
Next, right, you have the sequence. Variable yeah. Yoo-hoo! And you also got the nil.
Yeah, I mean, it's a list.
Yay! So see, this is an example which will have two implementations. Because both of them are...
Yeah, both of them are correct.
Yeah.
Both of them will be valid implementations. Yeah, like going from a tuple of AB to an either AB, right? And you can either do left of the first or right of the second, right? That's the idea here.
I'm super excited.
Okay.
Okay, what time is it? Did the baby wake up?
We don't know.
How many rules do we have? Okay,
I don't know.
I'm asking you and you tell me if we have them, right?
How would I know?
I will tell. Okay, so did we do and on the right? We did.
Yes.
We done or on the right?
Yes.
This done. We have and on the left.
Yes.
Okay,
yes.
Let's stay with the... Let's order them on the right hand side. So on the right hand side... Okay, can you move this? Put it up so we know...
This one?
Yeah.
Like below the and here?
Yeah, so we on the right hand side we can have implication.
Yeah, we have all the constructors on the right hand side here. We're done.
Okay, done. And for the left hand side...
We're only looking at ands for now.
Okay, we have ands. Let's do
ors on the left hand side as well.
I think we can finish
I think it should be pretty similar, right?
This will create a branch, actually.
I don't care yet. So we need to match or here, right?
Yeah, I'm so excited. Okay, you made my day.
That's awesome.
Yeah.
Okay, that's all we need to do here.
Yeah.
And then here we have this, fine. So this
and
would be something like this, right?
No.
What do you mean no?
No, it's not a list.
Oh, it's a normal branch.
Yeah, the only one that creates a list
is the one that we already have?
one that we already is the only one that duplicates.
Okay, so I have a branch. So what's the name of the...
It will be... You have a branch. It will be like...
Yeah, I copied it. But like, what's the name?
It's called left or...
Okay. Okay, we'll see. Okay, and then what do we have on
You have to put
two things,
A
right?
heaps. Yeah.
But we need to remove it from it, right?
Yeah.
Maybe we need a helper.
Yeah.
Oh, it's just delete. I don't think you can get much shorter than that.
Delete and concatenate.
Yeah, well, like,
but now you just need to concatenate A.
Like this.
On one side, and then you need to have con on the right side of the sequent.
Yeah. Like this, right? And then the next is the same with B, right?
res. Okay. Yep. Sounds good. And now I have implication.
Wait. Unreachable. What do you mean?
But because this you need to have this res. It's better match with this one. You see?
No.
You have sequent hips con. So this part just res, or it's the other.
No, but
case.
it should. No.
It's the other case of that one.
Oh yeah, okay. See what you mean.
You
but
just need to delete.
Yeah, I know what you mean. But
yeah, like this. Isn't it? Isn't it?
I'm not sure why it's doing this. Oh, I see. Right, because okay, so the problem here is that this whole thing I think is unreachable. Because we're already handling all the cases here. There's no other case.
On the
So
right,
this,
but on the left?
it doesn't matter. Because on the left we're not matching with anything. So as soon as it's done with this, there is no way the code reaches here. So this needs to be the first thing or something.
Okay.
Right? And then if
neither of that,
if we don't match on the left hand side with any of the things that we're matching, then it means we've deconstructed the hypothesis as much as we can, and then it means that we're fine to look on the other side.
It shouldn't matter. Okay, we go now?
Yep.
Okay, and for the implication we have 4 cases.
So it's also here, like if we have an implication on the left hand side, right?
Yeah, but the trick is now you should find, it's not just match in. Well, yeah.
Okay, show me the rules.
So the rules are like, you need to look what you have on the left hand. So you need to search for an implication, right? But then you need to look what you have on the left hand side of the implication.
That's fine. You just need to look here. I'll show you in a second. Okay, so this is like so. I hate this.
It will not create. One will create branch.
It doesn't.
We have to split again here.
Wait. So okay, what do we have? Like, what's the first one that we need to look? So if
A can be on disjunction.
Okay, so let's do that first. So I think we can just do this. B and then goes to C here.
I think you forgot the point.
Yeah. I think we can just do this. And it's fine.
Let's do this. This will create a next.
So it's okay. And next.
It's called left or
imp. Okay.
Okay, and build derivation. So what you do, you delete that array.
Everything.
You delete
the whole thing, right?
The whole thing, and replace it with C implies B, and D implies with A implies C.
And you're watching my case there, right? Okay.
And B implies C.
That's all, and we keep the same conclusion.
Yeah. Okay, let's check
Let's
again.
see if it compiles. Yeah, it does.
I got the letters right? So you take the left.
Oh, I can rename them to help you.
Like, no, it's okay.
Okay. So C or D goes to B.
Yeah, it looks fine. This is okay.
C to B and D to B. So A to C and B to C. Yep.
Okay, let's check. Let's write the same, but you have this conjunction.
Okay.
And then you need to delete it, and then replace it with this time just one. You get, it's like anchoring. A implies B implies C.
Oh. Like this?
Parentheses on the right?
Yes.
Okay. Let's do the hard one. If you have an implication on the left. Right. You need to you create a branch. Put the name of the
so what's this?
Left and imp. And the other is left imp imp. Yeah. you create a branch here.
Yeah, I'm just copying it over because I'm lazy. Okay.
Then delete it from here.
I will afterwards. I can delete it now.
Okay. And on the left hand side,
so we remove it
either way.
Yeah.
First, on the left hand side, you add, okay, so you have A implies B implies C. You have B implies C.
Okay.
And A. And on the other one, you get C.
Just
you
C?
add C. Yeah, let's look at this.
Like this?
Yeah. Okay, let's look at this. So I wrote it C implies D implies. Can you check? Okay, so we have C implies.
Okay, and then you want to do D implies B, which is B implies C, yes.
You get this C. Oh, and here it modifies the con.
Okay, how?
It's
just D, right? Which was D
B.
for us? It's B.
I think we got everybody confused now.
So here is B, right?
Yeah.
And then we have con here, right?
Yeah, con.
Okay.
Same. And here you get C.
So what's the problem? Oh, yeah. Everything's good. Fixed. Okay.
And we have just one rule.
The 0, 1?
The 0, 1, which says.
Okay.
And this is a tricky point. Here it might get stuck.
Because it's been a breeze so far. Okay, it's fine. We got it.
Okay.
So which one is it? Because I'm not
this one.
saying it.
We look at this.
Okay.
So we want on the left hand side of the implication to have a variable.
Oh, you need a function and the variable as well, right? You need to see if you can apply it to get the
somehow,
B.
Yeah. But I think it's easy. And it gets stuck. So I would say
okay, so we need to find the function, and then we also need to find the
P. And if you don't find it, you get stuck and you leave it stuck like this.
You just create a leaf with whatever you have, right? That's what stuck is.
No.
Yes.
You don't create a leaf.
Yes.
Yeah, but not necessarily, because from how you wrote the rules, you could...
We don't have any rule matching leaves. We stop at leaves.
Yeah, I know, but... Yeah, okay.
We just don't call it recursively and we stop.
Yeah.
It's fine.
But that will be the other matching case for the implication. Okay, I see how we write.
So we remove this and we have if
variable.
A goes to B.
But put it variable. Can you write it variable A implies B?
Oh, because you want specifically to only to be like a simple. Okay. Okay.
And now.
And we want.
You want to search A in hypes.
So I think.
And you have two cases.
Wait. Let me think.
Let me tell you. And then you can think.
Oh, right. I think I know. Never mind. So you want to do something like case.
So you want to find A in hypes.
Find what? Isn't there like an equality find? Like a lamb or something? Yeah. Case is an element in hips, right? Of nothing. We just do leaf of
put the sequent.
Everything, which is yeah, I think so. I think
put
we have
name.
it. Yeah, okay. What name? Leaf doesn't have a rule name, I don't think. Should it have?
No, it shouldn't. Okay, it's
No,
good.
leaf doesn't have a rule
Okay.
name.
And this will
Should it have a rule name?
It shouldn't. It's
No.
fine. And this will not be a derivation
I mean, shouldn't
tree.
because we have two ways
It
to
will
get
not
to
be
a
a
leaf.
proof. No,
Shouldn't we have a
it's
like
okay.
it's this rule versus this rule
No,
who
it's
created
okay.
a leaf?
It's okay.
Okay. Okay, and if we have it, but we don't care about it, right? It's just if it exists.
If it exists,
Then we create it's just a next, right? With l imps l0
Wait.
imp the CQ over build derivation.
Right, and now delete the implication.
But why? Oh, because we don't want to match it again.
Yeah.
Yeah, because we've that makes sense.
You said it.
What did I say?
Initially, I said okay, just leave it there and then.
No, here, yeah.
Okay, so delete the implication.
And then we need to add the.
And then we need to add B.
B. Yeah, just B. That's right.
Mm-hmm. That should be our Sequent Calculus. Ta-da-da-da, we're done. Okay, I have an example you should test.
Huh? Oh, oh, and this is just pure because it's just a single.
Okay. You should. Let's check this example. And then we go check on the baby.
Yep.
If it will stop on this and will not loop, then I think we're on the good track. Check this.
Oh, you want to have a sequence already, not a formula.
Doesn't matter. I can write it as a
No,
formula.
it's fine. But we need to remove this from here, right? We're just building a derivation from a sequence, right? Yeah, we need to remove everything. You know what? Let's make our lives slightly easier. Okay, so okay, so we want what?
Okay, let's write
var
A and
q.
B.
Ah, it's fine. It's fine. No, don't, because it's going to be slower. For p
Price R.
I don't even need this because it's an array, so we
But
can
you
just
should
do
write
this. Yeah, like this. Okay, and then var q
Var R.
and var r var p, and that's our thing. And then we do this into var p. Huh? Okay.
I think you forgot one parenthesis here.
Oh yeah.
Already a leaf? No. See, that's the problem.
What's the
Okay,
problem?
so that's the problem. I know what it did. It got stuck. It didn't know the result.
Oh, it got stuck from the beginning, or what?
I think, yeah.
Oh yeah,
Okay.
he didn't do anything. Yeah, not even one step.
No, he did one step. He had a leaf. Okay, he had a leaf.
Yeah, yeah, like it
Okay, so
jumped
what's
straight to
the
the leaf.
point here? Let's look at the rule. Right, so what we wanted to do is just first apply this imp left imp, right,
Okay.
in order to what was this one? And split it into no. Wait, left imp.
Yeah, left imp and to get. Oh yeah, and why didn't it find that?
Okay, so we want to apply left imp, and we would get P implies R, Q, Q implies R, R implies P, implies P. And then the other one would be R. Anyway, needed to create a branch here. R, or this guy here, implies P.
Wait, so what? How would it even know how to solve this though?
It knows.
How? So you're saying that from that it knows to do A to B to C, okay, and then it tries to prove. But why didn't it match that rule? Like the imp rule.
So what he got into here.
This one. But it did that before. It did that before finding this one, which I have no idea why.
Did you write match imp?
I mean, of course I did.
Yeah, but you wrote it in an imp. Good job, laddie.
Okay, let's have another look here. Okay.
You can't delete them.
No. Okay, so we have a branch.
Yeah, it applied imp.
Okay, and then we don't care about the sequent here. Where is my thing? Okay, it's here. And then it applied our 0 imp.
Yeah, that's good. Search the diff. Yeah, it's good. It will get us the derivation.
And then our 0 imp again. And then our 0 imp again.
Yeah. And then
it found a leaf which says that QR.
And then you also need that leaf, because check that the other leaf is from this branch here.
Yeah, because like this, you see, this is the parentheses.
Let's look at this leaf. It has a P. Is this a valid leaf?
We have QR.
No.
R implies.
It's not good. But here it was supposed to continue.
So let's look at this sequence then. So it's an implication
So here,
QR.
Here was supposed to do. It was supposed to do R. Q implies R. R implies P implies P. And here he was supposed to.
But it doesn't have.
Look at the exam. Look at the blackboard. Right? He was supposed to get. Do you have this?
So I have R. I have R implies P.
R implies P.
And I have Q implies R. Yes.
And P on the right.
Yes.
That's good. And now he's supposed to find this R implies P and this R.
No, but it will find Q implies R first because that's the first one.
Yeah, but you need to
and
look
it will
this.
stop. So you need to look at all of them, not just one, not the first.
You need to see if any of them applies, not just the first one. Yeah. Don't you have like?
But then this is again we're doing the list branch thing, and we need one of them too, or just a normal branch or something.
This is the simple case. So is supposed to find this, and then we'll get what he will get? He will get R, P, Q implies R, implies P. And here, okay, and this is again another problem with our problem, because we will try to yeah, we have a problem with implementation, because, okay, suppose we fix and he will do this step, but then when he gets to this, he will try to break this implication and he wouldn't fail. But actually, what we wanted to stop because we have this.
But it doesn't matter because it will stop anyway, and then we'll find P and P. So that's fine. No. We don't care about that one.
Yeah. Okay, we don't care.
Right, because as long as we don't have a queue, there's nowhere to progress. So then we'll stop and then we check. So that's the problem, that we need basically to. And but like, what if you have two different ones there? Like, what if you have two formulas that you could apply? Oh, do you just do a next? No, because you're kind of, you're branching. If you have two that you could apply, it doesn't matter the order you choose. Okay? But here, he didn't check if he could apply with all of them. If you have several that you could choose, doesn't matter. But here, he didn't went. So the problem is
he found
here,
don't
right?
You have like a find all or something? Can you just repeat that? Can you take all of them or somehow?
But then how do I take all and then only take the one for which this is true?
Yeah. If there is one for which it is true. I think we should go on check on the baby.
Yeah, I guess
we need to fix this,
here.
But I want to. This is not homework for you. Let's think about it together.
That's simple. It's just like writing some array functions.
Yeah. That's a tricky example. I got it from a book, so I know it's tricky.
Okay. So yeah. Okay, sure. I can figure this out.
But later. You should do a pretty printer.
Mm-hmm. Wait, did I not add it? I added it. Okay. So everything is pushed on the repository. You can have a look and play with it if you want. So yeah, we will stop now.
I will see you next week.
Mm-hmm. And I'll see you tomorrow. I don't know what I'll do tomorrow. I'll see. Probably some Haskell.
Yay.
Okay. Thank you, everyone.
Thanks. Bye.
See you tomorrow. Bye bye.
Bye. Want to rate something? Let's see, is anybody live? Nope, I don't think anybody's live right now. Let me have a quick look. Oh, Vince is live. Yeah. Okay, let's rate Vince then. Although I'm not sure a lot of people are still here. Actually, let's test because last time this didn't work. Yeah.
We couldn't rate Vince when we tried last. Where is it? Raid. There we go. Okay, so let's rate Vince. I think he's doing some Haskell. Okay.
Okay.
Bye bye everyone.
See you.